So here we go. Let's just start it. So I'm recording my notes as well. So I'm going to go over what we had last part of the last session, and I'll show everything on what we have on the slide. So make sure kind of you're following those, because that's what you probably will do on your paper. And then we'll do it in Excel. Hopefully tomorrow we'll try the math out. Remember, we had two plates parallel to each other. The top plate remains fixed. The bottom plate suddenly starts moving at 40 meters per second to one side. And this is the Navier-Stokes equation. If you drop those terms that we don't want, it's a 1D transient case. So we end up having del U over del T equal to kinematic viscosity, second derivative of U with respect to Y. We have a value for kinematic viscosity, assuming we know the fluid, which is oil. And this is our initial condition, that at time equals 0, at the starting time, T equals 0, the bottom plate is at U equal maximum U, which is 40 meters per second, and the top plate is stationary, so it's not moving. And boundary condition that at any time the top plate or fluids at the top plate remains again at U equals 0, and fluid on the bottom plate at U equals 0 travels at the speed of the plate, right? That's how fast we go. And so let me kind of start from here. So we are going to create a grid point, something like this. If your horizontal axis showing you time, and we're going to divide it into several spaces that each showing our delta t, and we march in time by increasing delta t. And the vertical axis is our y, which the maximum on top showing the location of the top plate. Here is the location of the bottom plate. And here we also can put nodes, which the distance between each two is our delta y. You can call it j equal to 0, the one in the bottom, which is supposed to move. J equal 1, next node. J equal 2, all the way to j equal, you can call it j and maximum j, which you can pick it 8 or smaller or higher. So I can show it something like this. I can make it grid points. And so this is our kind of grid points. One axis is time, one axis is y. Make sense so far? We had everything so far, really, nothing new. So last session we talked about explicit using forward in time central space. So explicit so if you remember forward in time central space applying on our main equation, which is del U over del T equal to kinematic viscosity, second U over del Y squared. That means that forward difference in time, which is the left-hand side term, and central is facing on the right-hand side term. So easy to follow. So we showed that if I apply the forward finite difference in time on the left-hand side, I end up having ui at n plus 1 minus ui at n divided by delta t. On the right-hand side, central space, I will have kinematic viscosity, which is constant, remains the same, times delta y to the power of 2, and divided termed by delta y to the power of 2. And then on top, I have ui plus 1 minus 2 ui plus ui minus 1. All of them at time step n, which is known. And we showed that that's our only unknown. Everything else is known because really we're using explicit method. So my final form of equation that I'm going to use in my finite difference is ui at next time step at n plus 1 equal to velocity of the fluid at the same node at the previous time step, ui at n plus kinematic viscosity times delta t divided by del y squared, nu delta t divided by delta y squared, which we call this d at the end, times ui plus 1 minus 2 ui plus ui minus 1, all at n time steps. So I guess I'm going to repeat one more time. Those n plus 1 and n refers to time step. And those I plus 1, I minus 1 refers to the nodal space in y or x direction. Now that I have this, any questions so far on this? I'm reviewing, but if you have any questions, just pause. No? Now I'm going to go to the next slide and show you what I'm going to do. So this is how you solve it on paper, really. That we're saying that, remember that two parallel plates that has a distance of 40 millimeter or 0.04 meter. Let's have y. So the maximum on top is 0.04 if you start from the bottom, which is 0. And the one at the bottom plate is 0 in y. So that's where we start actually. And depending on our delta y, you can have, if my delta y is, for example, is 0.005, for example, I think it takes 8 of those to make 0.05, if I'm not wrong. Yes. So the next one would be 0.035, for example. Then the one below would be this. I will have this all the way to 0. Which you can call it with a J as well. that J0 is 1, J at the bottom is 1. Let me show this one as well. Then I have 1, bottom one is 0, then I have 1. Keep going up, I have maximum 1, which is going to be 7, 8, and 9. So this is kind of showing my Y. And now I need to, on top, I'm going to show my time. And underneath here, I'm going to show my values, velocity values, because I'm trying to find U, correct? So I can talk about N as time steps. So initially 0, and then go to next time step 1, n equal 2, n equal 3, higher, or I can show it in the form of delta t. So 0 delta t, which is 0, 1 delta t, 2 delta t, 3 delta t, all the way to my t max. All the way to my, okay, who has a remote again? No, nobody. T max. This is my max n. Okay. Everybody following so far? Now, what's the highlighter? What this column should be called? Say that again. Initial condition, because that's the given information at times at t equals 0. And if either it's given or if not, we're assuming an initial condition, right? So the PDE, this is explicit, we need to have some initial condition. But in our case, it's given. We're saying that at the time equals 0, all the floors and plates are at 0, and at t equals 0, which is our initial condition, we start pulling the bottom plate. So everywhere else is 0, except the bottom plate, which is 40 meters per second, which is my initial condition on the bottom plate. Again, given by the problem. And we also have information on the bottom plate, which is my j equals 0 on this one, and top plate. What is the value of velocity on top plate? 0 all the time. So I can go ahead, put 0 no matter as I'm marching in time. And the bottom plate, you're saying that we are pulling the bottom plate at 40 meters per second constantly. So that's 40, 40, 40 all the time as well. Now, we need to, so far, we have the initial condition in, boundary condition on top and bottom. Now, all we need to do is that start writing or start calculating for each nodal values for each nodes at delta t equal 1, delta t equal 2 all the way forward. And what equation we're using? We're using this equation, which is the forward in time, central space using explicit method. So to find the velocity at node I in the next time step, we need the information from the previous time step. D is a constant because new kinematic viscosity is known, is given. We have a delta T, which we should talk about it. And then delta Y is a given, or we define it as well. So D is a number. Now on delta T, I think we talked about it. Let me, if I have room here, yeah, I can show it here. Now we talked about forward in time, central space, stability requirements. So who remembers what was the stability requirements for this method? Exactly. So this approach is stable if nu times delta t divided by delta y to the power of 2, which we also call it d, is less than or equal 0.5. Correct? Nu is given, that's the oil. We have a number for that, which is 0.00217. That's the kinematic viscosity for the oil. Delta Y, we picked it in a way that we have a number for, so we picked delta Y 0.005, or you can really choose whatever you want. And based on those, I can define my delta T, or time step, in a way that I can get a stable solution using it. So that's something you have to do in your, hopefully, in your work, show that if you choose this delta T or anything smaller than this, you will have a stable solution, and then you're gonna do your work based on that delta. Question on this? Following? So based on this, we show on delta T, I guess last session I did a better job in terms of this. So we said D, which is alpha delta T over delta Y squared, should be less than equal 0.5. Based on this, we find a maximum delta T, and we typically pick a delta T smaller than that. Now that I have a delta T, which makes my solution stable, I go ahead formulate for each cell. And if you're using a calculator to do this, let's do one of those, or at least try to show one of them here. To calculate this one, let's say, let's just start with this. To calculate this one, what we'll say, this is clear, we'll say that this value, ui, at time step 1 is equal to the value we have here, right? So this is n plus 1. Let me get a better color. So I guess I'm trying to apply this equation here. We need ui at n, which is this, plus d, which is a constant because we have nu delta t delta y. Again, this is my d. And now I'm going to multiply it by ui plus 1 minus 2 times ui plus ui minus 1. Ui plus 1 is all the way from previous time step, right? The value here, which for the previous time step was 0, so I have that. Let me show you this, minus 2 times ui, which is here, plus ui plus 1 or minus 1, which is this one really. I guess last one was ui plus 1. This should be ui minus 1. And now when you hit the enter, your calculator, you should get a number. This is your new value for you at this time step. And you have to do this, and then repeat this in 5 minutes. And typically, after doing this, you should be able, delta t, yes, you should be able to show a plot like this, that this is your h, this is your h, or this is your y direction, this is your velocity, and probably initially everything was initial condition. You had 40 on the very bottom plate, everything else 0. And as delta t increase, you have more converged results. And then you have, at the last time step, you have this as your velocity, for example. So typically, this is what we expect on kind of on a paper, which requires a lot of work, but you should be able to follow those formulations on each cell using the information from the previous slides. Now, question.
Could you just tell us how many iterations there, or is it just?
Yeah, probably I should tell, but really on a paper, if you show one of them and mention that hey, you have to apply this for a second one, that's really what we want. Any other questions? Is it easy to follow? Kind of really reviewed what we had last session. Now I'm going to do this quickly in Excel. Or I've done it here anyway, but I can do it so everybody can follow. Is that what you want? Enable editing. Okay. Let me do it from scratch. Over here. Move or copy, create a copy. Okay. So I'm going to delete everything here. So far, if you look at what we have here, in this section, what we have, I said, between two plates, I'm going to divide it into 8 sections. So my n is 8. So the maximum height, lowercase h, is 40 millimeter or 0.04 meter. The u sub 0, which is my boundary condition on the bottom plate, is 40 meter per second. Kinematic viscosity of the oil, I'm going to solve it for up to 1.08 seconds. So that's my maximum t. So this way, if you know your delta t and you know your maximum t, you know how many time steps you want to move on. And time, I picked my delta y the way I wanted. So actually, if I divide maximum height by number of sections, I get my y. or you can do it the other way. Define your y, and then you can see how many n sections you have. Delta y squared comes handy later. And based on stability criteria that d should be less than 0.5, I have my periodic viscosity and delta y. Based on this, I take my maximum delta t and I go a little bit below this to pick my delta. So I'm assuming 30% of that point of that question go just to this. And expecting half of the class? No, I'm confident. Everybody got it. So my delta t max is 0.05760. Everything else, I just picked the 0.05 portion of it. So kind of that's enough. Or you can go less than this, for example, just to be very safe. So based on this, your d will change. D, again, is function of new delta t, delta y squared. So now that I have this, I make my y the way I showed in the PowerPoint on the screen earlier. So my maximum height is here. Minimum is here in between. The way I do it is that I take the top cell minus delta y and then just dragging the formula down. So it's uniform. I kind of highlighted the boundary conditions with blue just to kind of make sure I'm treating those as a boundary condition. And let's say this is my initial condition. I'm going to highlight it yellow, right? So on top, velocity is 0. For the initial condition, everything else is 0, except the bottom plate, which is 40. And you can do some nice work as well. Put everything in the middle, but no extra credit for that, sorry. And what I can do, I can copy and paste this for other cells for the top and bottom. So to do this, I just realized that if I do pick this 40, hit F4, so I'm using the $sign. If you're familiar with this, it locked the cell. So when I copy and paste it to wherever I want, it just keep it there. It just doesn't move the cell. I can show you what I did. So let's say I define U upper surface, which is 0 here instead of typing 0. I put it here and I hit F4. So I put a $sign before the letter, $sign before the number, so makes it lock. I copy it, and I hold Shift, Control, arrow to the right, and paste it. So actually it's applied. I mean, you could really copy 0 as well, but it was giving me a little bit hard time. So this is better. Now that I have this, let me save it quick. I am going to write the formula that I had here on the next time step, right? So if I'm going to start from here, that's equal to UIN, so which is same J or I, but at the previous time step, plus B. I pick it from here. I hit F4 because I'm going to lock that cell, plus the top neighbor, plus bottom neighbor minus 2 times the same cell, which is F10. And that's it. What did I do? So, what happened?
You just put in a product operator between the 11 and the.
Here. Yes? Yes, okay. Yes, that's right. So that's what I have here. And I believe I can simply apply it here. So as you can see, for the first time step, you could see some effect of that moving plate on the next cell, but not applied to the others yet. So really on this one, again, this is the explicit simple one. This should be working. I don't know how many I have, but that should be enough. So this is a plot actually showing that as you march in time, so delta T, 2 delta T, 3 delta T, 4 delta T, you could see that the effect of moving plate slowly applies to the higher fluids, start moving, and the y-axis is your height along the y direction. This is your velocity along the x direction. And you can see that at different time steps, you have different values, and that should be a converged one. So this is the explicit, the simpler version. Now, question, let me know, otherwise we move to the implicit. It's a little bit different. I am going to, there you go. And let's not have my picture. How about that? Because you're seeing already once. Yes. Yes. Yeah, same as before. We're going to talk about the projects as well today. So let's start the implicit approach. Again, we talked about it, but how to solve it, we didn't talk. What's going on with my... Okay, this is better. So let's call this implicit method. And we talked about a few different methods in implicit. Lassonen, Crank-Nicholson, and the beta formulation, which is a combination of the methods we had in implicit. And what was the difference between implicit and explicit? What's that? Exactly. So you have more unknown parameters from next time step, 1 or 2 or 3. While explicit, as you mentioned, there's only one unknown, everything else is known. Going to the other side, it's really a matter of solving it. But implicit, you have multiple unknowns at the same time. That's why you need to solve them at the same time. So the appendix B that you have in front of you is showing how to solve implicit methods, focusing on Lassonen method, but as long as you follow those, this should apply to really any other method as well. So let's just start from here that formulation of most implicit method following this shape that A sub I U I minus 1 plus B sub I at time step n U I at time step n plus 1 plus C I at time step n U I plus 1 at next time step equal to DI at time step n. So this is typically how any implicit method looks like. Now what we need to do, we need to apply this equation to all nodes in advanced level. What do we mean by advanced level? Means next time step, right? So and if we do so, we can come up with the form of a matrix. So form a matrix for coefficients that we will see we end up getting tridiagonal matrix by just having the values of AI, BI, CI, and as you can see, those are from time step n, which means that they are known. So those coefficients are known, correct? Because first time step, initial guess, you can have all of those, and every time step you move forward, you have it from previous time step. So AI, B sub I, C sub I, D sub I are known. We should have those. Now, from now on, I am going to focus on, let's see here, Lassanen method, which is kind of question 312. By the way, finally, I uploaded those two chapters I promised. I did it before the end of the semester. So you have those, but I think we covered all chapter 2 and a big portion of chapter 3. So not all chapter 3. The last part is kind of considered for us. Now, if you look at the equation that we went through this before, for Lassanen method, we have D, and remember D was thermal diffusivity or kinematic viscosity, depending on if it's a heat transfer or fluid mechanics, times delta T divided by delta Y squared, right? That's the D, times UI minus 1, time step n plus 1, minus 2D plus 1, UI n plus 1, plus D UI plus 1 at n plus 1 equal to minus UIN. So this is equation 312 of the textbook, and that's something we covered before. I don't think I had it down there, but if you look at the Crank-Nicholson method, you can rearrange those and have it in this form. So you can see we are putting that equation into this form, right? Make sense? So my D is A, then B is minus 2D plus 1, and C is another D, and capital D right-hand side is minus UI. Again, anything at time step n supposed to be known. So comparing these two equations, which is from the handout you have on the appendix, which is B1 and B2. I have A equal, what is A? D, there you go, because this is this, which is a coefficient of UI minus 1. D equal minus 2D plus 1. What happened? Minus 2D plus 1. C equal another D. And D is my right hand side, because sometimes it's not simply minus UI. If you have a boundary condition, if you're close to the boundary, you have more than this. You have to add another boundary to cover that. So are you following so far? Yes. So again, this is a general form. For this approach, we can show it. This is going to be in this form, that A, B, C, and D have a known value. Now, next step, I need to apply this equation, B2. I need to apply this equation to all grid points. And for my matrix A times matrix column matrix U equal to matrix right-hand side, which is D. And then I need to inverse the matrix A and somehow link my column matrix D on the right-hand side to the one step back of the information we have from the solution. And then we have a kind of iterative answer that we can apply to all different time steps. And we will see later that in our plots, by increasing the delta t as we go in time, we get a more converged solution until we have a nice solution which is close to real answer, analytical solution. So now, next step is to apply this equation into all grid points, which we call this equation B2, that you have it here as well in your handout. So apply D2 to all grid points. I am going to write it quickly here as well. D times UI minus 1 minus 2D plus 1 UI plus D at UI plus 1 equal to minus UI for now. Good. So this is my question. Now, remember our example of two plates. We don't want to apply to that now, but just to keep it as an example, the bottom plate, we call it U equals 0, I or J equals 0, and as we go delta Y along the Y direction, we go from I equals 0 to I equals 1, or J equals 1, J equals 2, J equals 3, all the way to the top plate, which was, H was 40 millimeter, correct? So here, I start with I equal 2. And if I start from I equal to and then I'm going to apply the I here and write it here. Let me do the first for myself, and probably you can help me with the next one. So I have D times I minus 1, which is 2 minus 1, is U1, kind of N plus 1. Let's not show N plus 1 here, because later we're going to say anything on the left-hand side is at N plus 1. But we know that those are from next time step. Minus, again, D is a constant. So I have minus 2D plus 1 times U2, because I is 2 in this case, plus D times U3. This should be plus 1, right? Equal to minus U2. Make sense? And so this is my bottom plate, this is my top plate. Let's assume this is I equal 1, and then this is I equal 2, this is I equal 3, which later we showed with, previously we showed with J. They're the same really, and this is the maximum I. Now let's do it for next I3, and I will have D UI minus 1 is DU2 minus 2D plus 1 U3 plus DU4 equal to minus U3. Question here? Can we move on? So depending on how many really nodes you have along the Y, we can move on. But let's go, let's see how many I have. Let's go one more. At I equal 4, I have DU4 minus 1 is 3 minus 2D plus 1 U4 plus DU5 equal to minus U4. Now, let's say my maximum, the one on top, is, I call it I, capital M, maximum I. Okay, that's my highest I, depending on number of nodes I have. In this case, I'm going to write first for IM minus 2, two nodes before that. So I have, so I can show that I'm skipping some steps. So for that, I have, help me with this, d times u I minus 1, which means u I m minus 3, right? Minus 2d plus 1 u I, which is I m minus 2 plus d u I plus 1, which is I m minus 1 equal to minus u I m minus 2. And one to the last, which we call it I m minus 1, is d times u I minus 1 makes it I m minus 2 minus 2d plus 1 u I m minus 1 itself plus d u I m minus nothing. So du I m equal to minus u I m minus 1. There you go. I hope you're following. Yes. You should follow this because I'm going to apply the boundary condition on the top and bottom. And this should make sense. So we can really go form a table and solve it. This is my friend over there. What's that? Oh. He's usually nodding his head, said I understood. I always tending to look at this way because he is responding to me. Okay. Now let's apply the boundary condition here and make sure it makes sense. So look at I equal 2. Look at this one. And later we're going to apply boundary condition here as well. Again, you have to make sure it makes sense before, because if you go home, just probably spend a lot of time on this. It's going to be hard. And hopefully I can upload the video so you can repeat, watch it. Great. So let's look at I equal 2 and stop me if it's not clear. I have a D. D is known, right? I'm not worried about D because D is kinematic viscosity, delta T divided by delta Y squared. And when I know delta T, delta Y, and oil kinematic viscosity in my case, then I have a 0.4 something, a number for D. So a number times U1 minus a number times U2 plus D times U sub 3 equal to minus U sub 2. And what is U1? Yes. U1 is the velocity of the first U, first I, or J in the previous example, let's call it J as well, they're the same. Which is, we said it's gonna move at 40 meters per second at t equals 0, right, onward. So U1 is 40 meters per second if we consider the previous example, or a boundary condition because it's given. Makes sense? Anyways, it's known, which means that all known parts will go to right-hand side. So I'm gonna bring this one here. So my new equation looks like this. Minus 2d plus 1 times u2 plus du3 equal to minus u2 minus du1 and u1 for velocity at grid point 1 is kind of boundary condition 40 meters per second based on that example, or it can be any number. So this is how I treat really the one close to the lower boundary condition. And I also need to treat the last one here, which is IM minus 1. Let's assume this is your maximum top plate, which we call it maximum I or I capital M. This is my IM minus 1 before that, right? And if you look at this, I have d IM minus 2, which is here, minus 2d plus 1 u times IM minus 1 plus d times UIM equal to that. Which one is boundary condition? Exactly. So UIM is given, and that's equal to 0 because that's the velocity of the fluid on the top surface upper boundary condition. Make sense? So this is the U sub IM, right? Velocity at node IM, which is my top one. So this section is known. That means that this should go to the right-hand side as well. So my new form of last algebraic equation would be d times UIM minus 2 minus 2d plus 1 UIM minus 1 equal to minus UIM minus 1 minus DUIM. What is UIM in our example? 0. Is that what you said? So this is the, I think this is the main part of it. Actually, if you know how many I's you have, you can write down. So probably in an exam, I don't go crazy, give you I-20, hopefully. I might, but hopefully not. So probably 4 or 5. So you should be able to write, starting from I equal 1, 2, 3, 4, 5. Write those equations. And the one before the top boundary conditions, top boundary, this one, and the one above the bottom boundary, this one, you should do that simplification, which means that if a term has a value from the boundary condition, which is known, you should put it in, and because this term and this term are known, you should bring it to the right-hand side. Left-hand side, we're gonna just keep those with unknowns. Make sense? So instead of this equation, I'm using this green one, and close to the top, instead of this equation, I'm using this one. That's why I don't have I equal 1. I equal 1 belongs to the top surface, which I know is going to be 0. So I'm going to impose that boundary condition later, 0, 0, 0. And I equal IM is also another boundary condition, right? Which is the fluid on the bottom plate, which moves at the speed of the plate. Question? No? Are you sure? So, yes, there you go. Yeah.
Can you explain again why you dropped the n+1 notation?
N+1, you can add it, but I end up writing a lot of n+1, n+1, or I can say anything on the left-hand side is unknown, which is next time step, I don't have the solution. Anything on the right-hand side is known, which is from n. So from this step forward, I kind of know that these belongs to n+1 because I kept the unknown portion on the left-hand side of the equation, and right-hand side, which is from time step n, which is known, because I start with initial condition. I know that, I assume something. Everything goes to the right-hand side. So actually, I'm saying that we know that everything on the left-hand side is n+1, so I'm not going to write it again and again. But yes, left-hand side belongs to n+1, right-hand side n. Now, let me write the boundary condition. And that u at I equal 1, which is the lower boundary condition, is known, which is equal to 40 meters per second, right, in that example. And also u at maximum I, again, depending on what delta y you pick, you can have 8 or 10 or 100 of those nodes along the y, which is my upper wall, is also known, which is equal to 0 meter per second. And if you remember, because I have a known value for my boundary condition, I call it Dirichlet boundary condition. And we had also Newman boundary condition. If you knew what's the value of del u over del y on that wall. But this is kind of more simpler one, Newman boundary condition. So let's stop up to here. Tomorrow, 8:30, we're going to finish this and make sure we master it.
Are we also going to be going over MATLAB tomorrow?
Yes. So first we're going to do Excel and then MATLAB.